Hello students, welcome to Engineers Academy. Do hit the subscribe button if you are here for the first time. Now let's solve this problem from chapter 16, Hibbeler Dynamics. The problem says that at the instant shown, the boomerang has an angular velocity of 4 radian per second and its mass center g has a velocity of 16 inches per second, and that Vg is making 30 degrees with the horizontal. It is said that determine the velocity of point B at this particular instant. When the line joining this AB has a 45-degree angle and the velocity of this point G is 6 inches per second and making 30 degrees, we need to find the velocity of this point B. So since it's the problem related to the relative motion, so we can write VB, the velocity of B vector will be equal to the velocity of G plus the velocity of the velocity of B relative to G. Always remember that this G will always come in the denominator here. So whatever velocity you guys write here, then that's subscript will come here, right? So the velocity of B and everything written here will come in the numerator here. So this is a shortcut for remembering this relative velocity equation. So VB is equal to Vg plus the velocity of B relative to this point G. Now to solve this problem, we need to think of the direction of these velocities. So we are unknown about the velocity of this point B since it is required to be determined. The direction of the velocity of point G is given. That velocity has a magnitude of 6 inches per second and making 30 degree with the horizontal. And this is the relative velocity of this point B with respect to G. So the relative velocity is always due to the circular motion of this point B about this point G. So we can always think of this relative velocity as if this boomerang is only rotating about this point G in a circular path. So we can consider this diagram for the velocity of B relative to G. So you guys can think of the velocity of B relative to G as a velocity of this point B as if this point B is rotating about the circumference of this circle. So this velocity is always due to the circular motion, or we can say that this velocity is always due to the angular velocity of the system. So we can say that the velocity of B relative to G, this will be equal to the cross product of omega times um, the position vector of B relative to A, or we can say that this will be the position vector. This will be the RB relative to G, right? This is RB relative to G. This is RB relative to G, and this will be the position vector from G to B. So let me draw that position vector from G to B here. So this is the position vector from G to B, and this position vector is in the horizontal direction. Since at this particular instant, this will be the RB relative to G, or this will be the position vector from G to B. So, and for the direction of omega, since this boomerang is revolving in this direction, so if we curl our right hand fingers in this direction, so the thumb will point out of the screen. So the thumb tells us that the direction of the omega is in the outward direction. So if this is our positive x and this is our positive y direction, so this means that the omega is in the positive k direction, and this omega is 4 radian per second. So we can write that this omega is plus 4 radian per second in the positive k direction. Cross product with the RB relative to G. So this is RB relative to G, and this is in the horizontal direction. And we are given this distance. This distance is 1.5 inches, and this angle is 45 degrees. So we need to find the magnitude of this vector which is from G to B. So how to find that magnitude? We are given this triangle, and here this angle is 45, this angle is 90, this is 45 degrees. Let me draw that triangle here. So this is that triangle, this is 90 degree, this is 45 degree, this is 45 degrees, and this is 1.5 inches. So this is the length of the magnitude of the R of B relative to G. So if this is 90 degrees, then this is the hypotenuse, and this 1.5 will be the cos component of this RBG. So we can say that RB of G cos of 45 degrees is equal to 1.5. We are considering this angle. So for this angle, this is the cos component. So RBG will be the magnitude of the relative position from G to B, or we can say that the position vector from G to B is 1.5 divided by cos of 45 degrees. So we can say that this is 1.5 divided by cos of 45. This gives us 2.121. So this is 2.121, and this will be in inches. Remember, since this is in inches, so this will be in inches as well. So now, since we know the magnitude of this, and this is in the horizontal direction, this is in the positive I direction, so we can write this as a Cartesian vector. So this will be 2.121 in the positive I. And since there is no component, it is in the horizontal direction, so its J component is 0. So we can write that this is 0 J. So now we can write that V of B relative to G, we need to multiply this with this and this. So 4 into this and K cross I. So here I have drawn this, so K cross I is always J. So 4 into 2.121, and K cross I is positive J, and this will become 0. So this is 0. So plus 0. So there is no need to write that 0. So 4 into 2.1, 4 into 2.121. So this is 8.484 J, and this will be in inches per second, remember. So now the magnitude of the relative velocity of B with respect to G is always this distance time omega. So this is that same, the magnitude will be always equals to R omega. And what will be the R? So R is this distance, and omega is this angular velocity. So this so this is 2.121, so 2.121 into omega, we got 8.484, and the direction is in the positive J. So since we are thinking of the velocity of this point B relative to this point G with due to that circular motion, so this velocity will always be tangent to the path of this point B. Since this point B is moving along the circular path, so the direction of this velocity will be tangent to this path. So at this particular instant, the direction of this VBG will be in this direction, that is in the positive Y direction. And after some angular displacement, if let's say this point B is somewhere here for this blue boomerang, then this is that point B, the new position of this point B after covering some angular displacement, then the direction of this VBG will be again perpendicular. So we can say that the direction of this velocity will always be perpendicular to RBG. So if this is RBG, so at this particular instant, VBG will be perpendicular to this vector. So you guys need to remember this, right? So here we can directly say that VBG is in the positive Y direction. After all that discussion, we come to the conclusion that the direction of this velocity will always be perpendicular to this vector. So this is VBG, this is VG, and we need to find VB. So now, and from the cross product, we also got the direction of this VBG in the positive J direction. So this is in the positive J. So before going to solve this, we can always think of the direction of this relative velocity, and the direction of this relative velocity will be perpendicular to that position vector joining these 2 points. So that will be always perpendicular. So now we can apply this equation. We can apply this equation in 3 methods. Basically, one is the vector method, the other one is the scalar method, and the other one is the geometric method. So I will use all these 3 methods to find the velocity of point B relative to point G. So first of all, we will use the vector method. So for the vector method, VB vector is equal to VG. So here, this is VG. So we need to write this velocity of G as a Cartesian vector, since this is vector. So this VG have one component in this direction, and it has one component in the upward direction. So the X component is the cos component, which is in the negative I direction, and this is in the positive J direction. So we can write that this VB has VG is 6 inches, so 6 cos of 30. This is the cos component here. This is the cos component, and this is the sine component. The cos component is in the negative I, so this is in the negative I, and we can write that 6 sine of 30. This is in the positive J. So this is the Cartesian vector representation of that VG. This is not VB, this is VG. Remember, this is VG. And similarly, now we know that the velocity of B relative to G is 8.484, and it is in the positive J. So we can write that this is let me write it here. It is 0I. This is 0I plus 8.484 J. So for the vector method, we need to add up both of these. So again, from this equation, we can see that Vg plus V of B relative to G, the sum of both of these will give us Vb. So we can write that this is Vb. So we need to add up I component with I. So that is minus 6 cos of 30 I, and this will become plus 6 sine of 30 plus 8.484, and this will be in the J. So let's find this. 6 cos of 30, this is minus 5.196, and the J term is 6 sine of 30 plus 8.484. This gives us plus 11.484 in the J. So this is velocity of B vector. VB has one component in the negative I, so VB will have one component. The absolute velocity of B has one component in the negative and one component in the positive, so that VB is somewhat acting like this. So let's represent that velocity. So that VB is somewhat acting like this. So this is that VB vector. And we can find the magnitude of VB. So VB in magnitude will be equal to, we can always apply the Pythagoras theorem, so taking the square of both of these, so that will be 5.196 square plus 11.484 square under the square root. This gives us 12.60, or we can say 12.605 inches per second. And we can find this angle theta as well, which that VB is making with the horizontal. So we can always apply the tan theta. So tan theta will be, so if we consider this is VBX and this is VBY, so tan theta will be VBY divided by VBX. So VBY is 11.484. This is VBY, this is VBX, divided by 5.196, and taking tan inverse. So we will be able to find that angle theta which it is making with the horizontal. So tan inverse 11.484 divided by 5.196. This gives us 65.655. So theta is equal to 65.655 degrees, or we can say it is approximately 65.66 degrees with the horizontal. So this is the vector method, right? We can find it by using the scalar method. So in the scalar method, we only add up the horizontal components with the horizontal and the vertical components with the verticals. So again, it's very easy. We can write that this is the cos component of this VG. Let me write that this is a 6 cos of 30 and this is 6 sine of 30. And similarly, we know the magnitude of this VBG, which is 8.484. So now again, if we apply that equation, which is the velocity of B equals to the velocity of G plus the velocity of B relative to G. So for scalar method, we need to consider only the x component. So we need to remove these arrowheads, and we will write this as x, this is x, and this is x. So we will add up all the x components. So to find the x component of VB, we will add up this, which is in the negative x direction. This is our positive x. So here we will have minus 6 cos of 30 and plus 0, since this is in the vertical direction. So this means that the x component of VB is the cos component of this VG, which we got here, right? This is minus 6 cos of 30. And similarly, for the y components of VB, we need to write that equation for y components. So we will add up. So the y component of the velocity of B will be this sine component plus this. So here we can see that this is 6 sine of 30 plus this. We got that same. We will get that same y component of VB. Now after this, we will discuss the third method. So the third method is the geometric method. So that is very interesting. Let me erase all these and then we will discuss. So again, for the geometric method, we will apply this, since this is the basic equation, and we will apply the head to tail rule. So for this, the velocity of G, the vector of velocity of G plus this vector will give us VB by head to tail rule, remember. So velocity of G is making 30 degree with the horizontal. So let me draw the diagram here. This is the velocity of G, which is making 30 degrees. So velocity of G plus the velocity of B relative to G. So the velocity of B relative to G is in the vertical direction, that is in the positive y. So by head to tail rule, we need to place the tail of the velocity of B relative to G here on the head of this VG. This is VG. This black vector is VG, and this is the velocity of B relative to G. So VG plus this will give us VB. So the resultant will be from the tail of this to the head of that vector. So this will be, this is the velocity of that point B, the absolute velocity of that point B. So now if I draw a horizontal line here, so if this angle is 30, then this angle is 30, this is 90. So we know this whole angle. So this whole angle is 90 plus 30, which is 120. So this whole angle is 120. Now to find the magnitude of this VB, we can apply the law of cosines. So for law of cosines, we can write that VB square is equal to VG square plus velocity of B relative to G square minus 2 VG into velocity of B relative to G cos of the included angle, right? So this is VB square is equal to VG square plus this square minus the product of these two cos of the included angle. We want to find the magnitude of VB. We need to take square root on both sides, so we will have VB. So this will be our VB magnitude, and this will be equal to, now I will do it directly in calculator. VG is VG magnitude is 6, right? VG magnitude is 6. Let me write that this is 6. This magnitude is given. This is 6 inches per second. And we know, we determined this magnitude, which is this 8.484. This is 8.484. So square root 6 square, 6 is VG, plus velocity of B relative to G is 8.484 square, minus 2 into 6 into 8.484 multiplied by cos of 120, and this gives us the same magnitude of VB. So VB is 12.604, and here we get that same magnitude. So 12.605 inches per second. Now we can find the angle of this VB as well, that angle theta, which we have just got 65.66 degrees. So this angle is at that angle theta. Let me write that this angle is that angle theta, and this angle theta will be equal to this angle plus this 30 degrees. So let's say that this internal angle is, let's say that this angle is angle alpha. So first of all, we need to find angle alpha, and then this angle theta will be equal to alpha plus 30 degrees. So we can apply sine's law to this triangle. So we can write that sine of alpha divided by the magnitude of the opposite side, which is VBG, which is 8.484, equals to sine of 120 degree. This sine of 120 degree divided by the magnitude of that opposite side, which is VB. So that is 12.605. And by cross multiplying both sides of equation with this, sine of alpha will be equal to, so sine of alpha will be this 8.484. So let's find the sine of alpha. So this will be sine of 120 multiplied by 8.484 divided by 12.605. This gives me this. So sine of alpha is equal to that answer. And then if we take sine inverse, so we will get that angle alpha. So let me take that sine inverse using calculator. So sine inverse of this answer gives me 35.65. So angle alpha is 35.65 degrees, and is this theta is alpha plus 30. So we need to add up 30 degree with this. We will get that angle theta. So this angle theta is 35.65 plus 30. So this will give us that 65.65, which is approximately 65.66 degrees, right? So we got that same angle theta, 65.66, and we got that same magnitude using this geometrical analysis, using the law of cosines and the law of sines. So this is how we can solve this relative motion problems, and this is quite interesting. I hope this will help you in your learning. Let me know in the comments if all this discussion helps you in your learning. Do subscribe Engineers Academy for the solution of such more problems from Engineering Dynamics by Hibbeler.